All right, guys, welcome to our lesson on what's called Gibbs free energy equation. Doesn't sound all that exciting, but really what we're going to be seeing here today is how this equation is going to allow us to predict whether or not a chemical reaction or a process will naturally occur on its own or not. Like, for example, I could ask, is the melting of ice, is that a naturally occurring process? Well, understanding this and the concepts we're talking about today, you'll be able to answer that. All right. So all chemical systems proceed naturally toward conditions of least enthalpy. You guys see delta H as enthalpy. Remember, you can kind of think of it like heat, right? It's chemical potential energy. And what we're saying is when the delta H in a chemical process or reaction is less than 0, right? You guys remember it's negative, delta H is negative. Remember, that means heat's lost. What are we talking about here? We're talking about exothermic reactions. So we're saying pretty much all things would tend to go from, and you guys know in an exothermic reaction, you have a state, the reactants have a high potential energy, and then they produce products which have a low potential energy. It goes from a higher energy state to a lower energy state. That energy is given off in the form of heat, okay? That's so when we say naturally, we're saying on their own or spontaneously would be another word we would use. Here I got a question. So then why do, if we're saying all chemical systems proceed naturally toward conditions in which you have, you know, essentially an exothermic reaction, so wouldn't that beg the question, so then why do endothermic reactions happen? You guys remember in an endothermic reaction, you start with low energy reactants and then you produce high energy products. How can that occur? Because we do have chemical reactions in which an endothermic process occurs. And the reason is because in determining whether or not a process or a reaction will occur, it's not only driven by enthalpy, so there must be some other driving force that can explain, for example, why endothermic reactions can naturally happen. And that's because there's another driving force which determines whether or not a process will happen, and that is not just enthalpy. There's two things we have to take into consideration: enthalpy and what's called entropy. So this is going to be new for you, a lot of you guys. All chemical systems proceed naturally toward conditions of greatest entropy. See how it's like the reverse. In this, they would tend to proceed to a place of lowest enthalpy, right? Chemical potential energy. But you also have to take into account that naturally it will go to conditions of greatest entropy. What's entropy, you ask? Entropy, we abbreviate it with an S, just like you guys remember enthalpy is abbreviated with big H. Big S is for entropy. Entropy is disorder or randomness. So what are we saying when we say this? This is really the second law of thermodynamics. All processes naturally go to a place of disorder, condition of disorder. So you'll start in a more ordered state, and then there's a strong tendency to go to a disordered state. It's kind of like your bedroom. You guys think about your bedroom. You guys think if you don't really do anything and you just over some time, maybe you guys are even noticing now with this whole distance learning, what do you notice over time is happening in your bedroom? Isn't it just getting messier and messier? It just naturally goes to a state of higher entropy or more disorder. Now, can you reverse that? Of course you can reverse that, right? But what does that require? It requires energy on your part. It requires energy on your part to say, okay, I'm going to put socks in the sock drawer. I'm going to put undies in the undie drawer. That requires energy. But naturally, which way does it proceed? From a state of order to disorder and increase in entropy. It's kind of like this. If we had a gas, and let's say we had this valve is open, I would ask you guys, what is the more likely scenario? How do you guys think you would see the gas molecules? Obviously, wouldn't you guys agree? They would be more like this. When the gas molecules wouldn't be sequestered all in one side. They wouldn't stay on one side. When you guys agree this is more ordered, they're all in one particular vessel. But what's naturally going to occur? They're going to naturally spread out and fill the available container to them. It would naturally go from a place of order to disorder. In fact, you guys know the only way you could get this is if you had that valve closed, right? Another thing here, which one would be the more likely scenario? Once again, gas molecules that move randomly. Wouldn't you guys agree? This is the most ordered state, slightly more disordered, and this is the most disordered state. This is how you would expect the gas molecules to arrange in proceeding to a state of more disorder, higher entropy. This is shown like like a magnet. When all magnetized elements, when they're all aligned in a very particular order, you can have a magnet. What happens when you drop a magnet? You misalign a lot of those. Well, you think about it, generally speaking, how would you guys expect things to exist in a state of disorder once again?
Let's look at a particle view of the endothermic process of ice.
think they're going to show ice melting. So here we have water molecules are in a nice ordered state, right, in the ice.
The disorder of substances is called entropy and is symbolized by S.
Okay. So here's, I believe it's ice. Yep.
How are the particles of the solid related to those of the liquid?
The particles of the liquid are more mobile and move more randomly. You might say that the particles of a liquid are more disordered than the particles of a solid.
So you guys, the process of melting would result is driven in a sense by an increase in entropy. Wouldn't you guys agree? In this state, in the liquid state, the water molecules are less ordered than they were in the solid state. So in this case, when you're calculating delta S for the process,
So we can say that for a substance, the entropy of its solid state is less than its liquid state, which in turn is less than its gaseous state.
so you guys see what we're saying here? You guys would agree in the solid state, the water molecules are pretty organized. It has a low entropy value. When it melts and becomes a liquid, now the molecules are free to move about each other. The entropy is greater than that of the solid. And then when you finally evaporate it, now the molecules can move freely. That would have a higher entropy value than the corresponding liquid.
Entropy changes, delta S, can be calculated in the same manner as enthalpy changes. There are tables that contain standard entropy values for many compounds.
So you guys, compounds, what they're saying is there is actual entropy values given to each compound that you can look up. But generally speaking, this is what we find to be the case.
Yes, the entropy change for a reaction can be calculated by subtracting the sum of entropy values for the reactants from the sum of the entropy values for the product.
So you guys, the delta S for a process or a reaction is done just like we would calculate delta H. We take in this case, we take the entropy values of the products minus the entropy values of the reactants. Products minus reactants, just like we did with delta H when we're doing enthalpy changes.
So if the process or reaction moves toward more disorder, then the entropy of the products is greater than that of the reactants.
Right, and so when you
And
calculate
delta S is positive.
when you calculate delta S, you're taking out large entropy value of disorder, subtracting a smaller value of more ordered reactants, and if you get a larger number minus a smaller number, you're going to get a positive value. That's what we would expect naturally occurring processes to do, is to have a positive delta S. Okay, let's look at some examples, guys, and see if you guys can determine
Can you
what the
predict the
delta S
sign
is.
of delta S for the following processes or reactions?
Here we're going to see
If you need help, click to see the particle view of the reaction or process.
we're going to see the process by which gaseous bromine is converted to liquid bromine. Okay, gaseous bromine, diatomic molecule. Molecules moving about freely, right? And what process are we seeing? We're seeing it become a liquid. That's the condensation process. So now if it went from a gas to a liquid, did the entropy increase or decrease? Hopefully you guys would realize the entropy, let's see.
The entropy decreases in this condensation process. Notice that the particles are closer and less disordered in the liquid phase.
So the amount of disorder, that's entropy, decreased. So therefore it would have a negative value. This is, you guys, sublimation. This is solid carbon dioxide, right? Dry ice. You guys know it goes directly from a solid to a gas. You guys, what would be the delta S for this process of sublimation? Think about it.
The entropy increases in this sublimation
You
process.
guys agree more disorder now?
There is much
From
more
solid
disorder
to a-
in the gas
to a gas.
phase.
Okay, let's look at taking solid salt and then we make it aqueous. So basically we're dissolving salt in water. You guys could probably already make a prediction. Think about solid salt, the positive and negative ions. And water, you guys remember the ions separate. So what happened to the entropy? Did entropy increase or decrease? Is delta S positive or negative?
The entropy increases during this dissolution process. The sodium and chloride ions have much more mobility, resulting in increased disorder when dissolved in water.
So guys, whenever you take a substance and you dissolve it in a liquid like a salt in water, the entropy will always increase. It's always going to become more disordered as the molecules are able to spread out. Okay, let's look at this situation. This is a chemical reaction. Check this out. We got 3 gas molecules, and then look, you're going to have breaking of bonds, formation of new bonds. We just went from 3 gas molecules to 2 gas molecules. Did the entropy or disorder increase or decrease? What do you think?
The entropy decreases during this reaction because the system goes from 3 moles of gas to 2 moles of gas.
So it stayed in the gas phase, but now there's less, we'll just say it became more ordered as it went from 3. So therefore the amount of disorder, which is the entropy, decreased. Okay, so you guys put this, the delta S, if you're going to calculate delta S, you just take the S of the products, the entropy of the products minus it, and then these are values you can look up on a chart. We're going to be doing that here shortly. Once again, so we would normally expect delta S to be greater than 0, but now you can go to a more ordered state, but you would have to do it unnaturally or with the input of external energy. By naturally, we're saying without any external other factors. Okay, so if we look at this reaction, here's a chemical reaction. Obviously, there's a rearrangement of atoms. Is the entropy increase, or decrease? What do you guys think? So if you look, well, hopefully you guys would realize it increases, because check this out, guys. We went from 3 moles of a gas and 1 mole of a liquid to 3 moles of a gas. We went from a gas and liquid to just purely gas. So that is an increase in disorder. The entropy increased. Okay, look at this, guys. We've got silver nitrate and hydrochloric acid. What's going to happen is you're going to have silver chloride precipitate out, and we have nitric acid left. What happened to the entropy? It decreased. You guys notice we went from 2 aqueous solutions, we actually formed a solid. That's pretty ordered, where those particles are in a very ordered state. So there was a decrease in disorder. Once again, you guys, 2 driving factors. We have to think about both of these.
We have 2 natural driving forces. The tendency to be exothermic and release heat,
High
and the
potential
tendency
energy, low
toward
potential
more
energy,
disorder.
and tendency to more disorder. So if we're going to be able to predict whether a process or reaction will occur, we have to take into account both of these factors. So we want to consider if the reactions are we call it thermodynamically favored. That's what we mean by spontaneous. It's going to happen on its own. So if you have a condition where the delta H is less than 0, that means it's negative, it's exothermic, and the entropy increases, that means it's disordered. You guys, will that occur or not? Always, it will always occur, because both factors contribute toward that occurring. What about if we have the delta H is greater than 0, meaning it's an endothermic reaction, and the delta S is less than 0? That means it's becoming less disordered or more ordered. Well, both of those would go against it occurring naturally, so you guys, that would never ever happen. And then we have a scenario in which we have an endothermic reaction, but the entropy increases, and then we also have a scenario where we have an exothermic reaction, but the entropy decreases. The question is, what about in this situation? Would those occur or not? The answer is it depends. So I was hoping to hear it. Normally I'd wait in class and see if you guys can come up with something. I can't really wait here, but what do you guys think it might depend on? What do a lot of these reactions you think depend on? What's a word we always bring up? Depends on temperature. You guys, this here is Gibbs free energy equation. You guys, the brilliance, I think this is my most favorite equation. There's power associated with it. If you know how to use it, you can predict whether or not a reaction, a process is going to occur or not. Notice the delta G. So what we do is calculate delta G, and based upon what delta G is, we can determine whether or not it's going to occur or not. The power of delta G is it incorporates both the enthalpy factor and the entropy factor, both, and then it also takes into account a factor which can affect whether it'll occur or not, and that's the temperature. Notice, you guys, whenever you put temperature in here, it has to be Kelvin. We have to use an absolute temperature scale. So if you guys see this, if delta G, when you guys plunge in delta H values for a process and delta S values and take into account the temperature, and you get a value, if your value, delta G, is less than 0, if it's negative, what that means is negative. That means there's a lot. It's called the Gibbs free energy. It's the overall energy of a system that takes into account both enthalpy and entropy. If that's negative, that means there's a net lowering in the overall energy of the system. And what do you guys think? Will that occur or not? That's when it'll occur. So what do you do when you're using delta G, the Gibbs free energy equation? You're just trying to see if the value of delta G is less than 0 or more than 0. If it's less than 0, the process will occur. And you guys, like for example, check this out. You guys see why that is? Because check this out. Look, if enthalpy is less than 0, so that's negative. So this will be a negative value. And let's say entropy increases. That's a positive value. Now you guys, now check this out. You have this factor right here. Remember, temperature is in Kelvin, so what kind of values will we always have? We'll always have positive values. So you have a positive value times a positive value. What kind of value do you get? You get a positive value. Well, if you get a negative value minus another number, what kind of value are you going to get? You're going to get a negative. It will always occur. Now look at these other. Look at this one. Remember a situation that will never occur, right? When enthalpy increases, that means it's a endothermic reaction, and then also what we're seeing here is there's a decrease in disorder, so delta S is negative. Now here you guys are going to see why will that never occur? Well, just look at our values. Temperature is always positive. What's a positive number times a negative number? When you guys agree it's a negative number. You have a positive number minus a negative number, minus a negative. You guys know when you do minus a negative, won't that just be a positive value? Delta G would be positive, and therefore confirming that that process or reaction would never occur. Okay, now check this out, guys. What about if we have a situation where it's exothermic, which, right, that would be what we would, would drive a reaction naturally, but the delta S is less than 0. That means it's becoming more ordered, which goes against the natural process. So we kind of have the two forces which are in conflict with one another. So why do we say it depends? Well, look at it. Delta H is negative. Remember, what we're trying to do is calculate the value of delta G to determine if it's positive or negative. If it's negative, it occurs. If it's positive, it won't happen. So this is a negative value. And let's say delta S is negative. Okay? So now let's see what kind of result we get. Once again, what kind of result will we get here? Once again, temperature is always a positive value. Positive times a negative is a negative. So now look, when we take a minus a negative, what ultimately will happen to it? It'll become positive. So now we have a negative value and over a positive value. So you guys see when we say it depends, what does it depend on? Well, you guys think about it. In a scenario like this, if it just depends on whether or not this factor here, the positive value, is greater or less than this factor here, the negative value. Well, when will the positive value be, when will this value be greater than this value? When you guys agree? When the temperature is high. So when the temperature is high, when the temperature is high, that increases the value of this factor. So at high temperatures, this positive value will be greater than this negative value, and what will happen with delta G? It'll be a positive value. But what happens if the temperature is low? If the temperature is low, then this will be a positive value, but it's going to be a small positive value. So now in this case, the negative value will be greater than the positive value. So if your negative number is greater than your positive, overall what do you have? You have a negative value. So what would we say in this situation? Under low temperature conditions, it would be spontaneous, it would naturally occur. But under high temperature conditions, which increases this factor, this positive factor here, making the delta G positive, it would not happen. Okay, this is a question I'm going to ask you guys. So you guys see in this situation, this provides, right, it's exothermic, gives off energy, and in this situation, right, to make something more order, it requires energy. So when will it occur? Because this is important to know. This kind of helps us to understand when these two factors are in conflict. If enough energy is available from the bond breaking and forming, right, in an exothermic reaction, right, more energy was given off in the formation of bonds than was required in the breaking of bonds. So overall, it's a net loss of potential energy. If that energy is enough to do the order, because remember, it requires energy, just like it requires energy for you to clean up your room. If you have more than enough energy given off in the enthalpy change in the reaction to do the ordering, and there's still some left over, your reaction goes, it's spontaneous, it will occur. However, if the amount of energy given off, which is still an exothermic reaction, is not enough energy that's required to do the ordering, then that reaction would not occur. And that's what we're trying to figure out here when we're determining the sign on delta G. So you guys, we do need to practice one, because I don't want to give you guys an assignment without practicing. Okay, and so we talked about it can be spontaneous. Okay, here's what we're going to do, guys. We're going to answer this question. Okay, just a few more minutes here, guys. Is the decomposition of carbon dioxide, think about carbon dioxide, got carbon dioxide, is it spontaneous? That means will it occur on its own? Because we can get it to occur, right, if we input energy on that, but on its own at 25 degrees Celsius. And you guys notice I have to put a temperature because a lot of these processes are temperature dependent. And notice, okay, so in this case, what are we going to use? If I want to be able to predict whether or not a reaction is going to happen, what do I need to use? Right off the bat, you're putting Gibbs free energy equation. So you guys are going to have to, you don't even have to memorize, I believe it's on your formula sheet. Now I would, if I were you, I would try to make an equation that kind of shows what's going on. I'm showing the decomposition of carbon dioxide. What am I talking about here? I got carbon dioxide decomposing. What's it going to decompose into? Carbon and oxygen. So I'm wondering, will this reaction occur spontaneously at 25 degrees Celsius? So we're going to use Gibbs free energy. Remember, what I want to do is I want to solve for delta G and see what sign it is. So in order to get delta G, I'm going to have to calculate a delta H and a delta S. So let's do a delta H right now. Okay, look at delta H. Notice I gave you the enthalpy of formation for carbon dioxide. You look this up in a table. Okay, and you'll notice it's negative. What that means is when carbon dioxide is formed from carbon and oxygen, right? And remember, you only have enthalpies of formation for compounds, not pure elements. Pure elements, by definition, have a zero formation because from a science standpoint, those elements have always existed, but the compounds were formed from the constituent elements. And in this case, you'll notice as is the case with most enthalpies of formation, it's negative, indicating it's an exothermic reaction. Now, so what's the delta H for this reaction? Notice, when you guys look up in the chart, it's the enthalpy of formation. It's showing the formation of carbon dioxide. You know what it's showing? It's showing the reverse reaction. When carbon and oxygen come together to form carbon dioxide, negative 393 kilojoules of heat energy is given off per mole. But I want to show the decomposition. So what's the delta H going to be? Hopefully you guys know. Don't you just change the sign? If it's just the reverse reaction, you just change the sign. So it's plus 393 kilojoules per mole. Now you guys, I got to bring this up. This is very important. We're dealing with delta H and delta S. Your delta H values will typically be in kilojoules. Your S values will typically be in joules. Since we're using these together, we have to put one in terms of the other. So at this point, if I were you, I would just change this to joules. And you guys, kilojoule is 1,000 joules. So 393 kilojoules is a positive 393,000 joules. Because I'm going to have to use this later. I just anticipate that, so I convert it to joules. Now, what else do I have to calculate? I have to calculate a delta S. So you guys remember how to do delta S? Remember? You just get the entropy of the products minus the entropy of the reactants. So the products here, the entropy value for carbon is 5. Oh, you guys, this is kind of good to know too. Notice, look at the entropy values. You notice, look, as the substances get larger, right? We go from an element to a molecule to a compound. What do you see happens to the S values, the entropy values? You notice how they get larger. So there's a correlation between the entropy value and the complexity of the substance that you have the entropy value for. So anyways, I got my delta S. I'm going to get my products. Remember, it's always products minus reactants. So the entropy of my product is carbon is 5.8. So I go 5.8 plus, it's the sum of the entropy value of oxygen, which is 205. So that's the sum of my products minus that of the reactants. And what's the entropy value for carbon dioxide is 213.7. So I do that, and I already did it just to make life a little easier for me. It's negative 2.9, and notice the units. You guys, I don't write the unit on every one because that would be kind of sloppy. I just know that they're all joules per Kelvin mole. Okay, so now you guys have those values. What's the last thing I got to remember though? You guys, very, very important. You guys remember, you have a temperature. I'm not going to put 25 degrees in there. You guys remember what you got to do? That temperature has to be, and you know what will kind of clue you in? Look at the units here, Kelvin. You got to remember this has to be in Kelvin. You guys remember what you do to get Kelvin? Kelvin is simply the Celsius plus 273. So what's the Kelvin temperature? 25 plus 273 is 298 Kelvin. So now I have everything I need. I got my delta G is equal to my delta H, which is positive 393,000 joules per mole, minus the temperature, which is 298 K, times my delta S, which is right here, negative 2.9 joules per K mole. Notice, look at your units. Kelvin cancels with Kelvin, and then what do I have? Joules per mole, because that's what you're going to get. You're going to get a value in what's the delta G per mole of the substance that undergoes the reaction, right? So I plug that in, so I'm going to multiply those together, and I think you guys can already see a negative times a negative. You guys, this shouldn't be surprising either. The delta H is a positive value. Once again, you guys remember, energy is given off when carbon dioxide is formed, and that helps explain why there's a lot of carbon dioxide in the atmosphere. And obviously, to break it down, it's going to require a lot of energy. And then look at the delta S. It shouldn't be surprising that the delta S, let me see here, well, that's kind of interesting. Let me see, did I do that right? Yeah. No, I'm going to just leave it at, I don't want to confuse the issue with that. But nonetheless, okay, so we're going to plug those in, and what you're going to get is, you're going to get this huge number. Look at how big this number is compared to, this is going to be much smaller. It's going to be, either way, look, a negative times a negative is a positive, and a positive is 394,364 joules per mole. But you guys, what's the biggest thing? Even though we see that that's a pretty large magnitude, the main thing we're looking at is positive. So what that means is there is a net increase in the Gibbs free energy, that's what you're solving for, of the system. So would that happen? Will things naturally go from a state of, lower overall energy to higher overall energy on their own? It won't, and that shows you, and it definitely won't. Look at the size of that value, but the main thing is that you see the positive. So your answer to this is unequivocally no. You guys should have already been able to answer that, right? You guys think about it. Carbon dioxide, you guys, we've talked about before, carbon dioxide is a very stable compound. And what do you guys notice at 25 degrees Celsius? How would you guys describe 25 degrees Celsius? Isn't that like room temperature? You guys, carbon dioxide is not breaking down on its own. You remember, that's the problem with the environment and with the burning of fossil fuels. We produce a lot of carbon dioxide and it just stays in the environment. Really, what's the only thing taking the carbon dioxide out of the environment is plants that undergo an endothermic process of photosynthesis in which they ultimately convert it back into, right, oxygen and glucose. But on its own, will it spontaneously decay at room temperature? Absolutely not. How do you know that? The positive value of delta G, and not only that, it's an extremely large value saying no chance it's going to spontaneously break down on its own. All right, guys, thanks for joining me. We'll see you next time.